Okay, now we have an ideal gas that is trapped inside an isolated container. And the question of interest is that since the system is isolated, the total energy is not changing in time, but how is this energy distributed between molecules? So first thing I want to note here, it's an isolated system. So that is going to imply total energy E is a constant because there is no energy exchange mechanism with the environment. It's totally a closed system. Now I want to know what is the contribution to the total energy from these molecules. If you remember from your thermodynamics class, we have two possible cases we talk about, monatomic and polyatomic gas. So if you have a monatomic ideal gas, then we only have the motion of the atoms in x, y, and z-axis. So we have three translational degrees of freedom, and therefore the contribution from the ith molecule to the total energy is only the kinetic energy. So it's going to be 1 over 2 mvi square. So this epsilon I is the energy of the ith molecule. Since in this ideal gas we're assuming that all molecules are identical, m is mass of one molecule and vi is the speed of the ith molecule. So assuming that we have a monatomic ideal gas, the energy of the gas is basically composed of kinetic energies of individual molecules. Now what about the potential energy? Well, the potential energy would be present if you have interactions between molecules. So U potential energy is assumed to be 0 here. Basically the gravitational potential energy is also negligible because we have very small masses, and we can neglect the contribution from gravitations. Okay, so mg I'm going to neglect. So therefore I have free molecules. So remember, this was our assumption. They are not under the influence of any potential energy. So therefore, the only contribution to the total energy is the kinetic energy of the molecules. So with this scenario, I have the total energy E of the system is sum of the energies of all molecules, 1 over 2 mvi square. And if I ask myself what is the average energy of a molecule, it is epsilon bar, what is the average value of the energy of a molecule at equilibrium. So this is my question, how is the energy distributed? The answer is epsilon bar should be equal to the total energy divided by n, the number of molecules. So n, total number of molecules at equilibrium. This must be the case. Y, most random distribution of energy. Remember from our previous arguments, we're looking for the most random case at equilibrium, and this is the case when you have the energy distributed equally between molecules at equilibrium. So that implies the average value of epsilon I, 1 over 2m average value of Vi square must be equal to E divided by N at equilibrium, and average value of Vi is V average. Okay, so what is the average speed per molecule? How is this distributed? This average speed is the same for all molecules, but how about the average velocity? The average velocity must be 0 because I should have random direction of velocity. So once again, this is at equilibrium. So the average velocity is 0, but average speed is the same for all molecules. Now, as I said, we're talking about a monatomic ideal gas scenario here. How would this scenario change if you have a polyatomic ideal gas? In the case of a polyatomic ideal gas, you would consider contribution from rotations and possibly vibrations may contribute. If you remember which one contributes depends on the temperature of the system from your thermodynamics class. So we're going to postpone this discussion for later on in the semester, but basically keep in mind that if you have a polyatomic gas, what is a polyatomic gas? For example, if you have hydrogen gas, oxygen gas, etc., you should consider the possible contribution from rotations and vibrations. If you have monatomic gas, for example, helium, argon, etc., examples, we can only consider the kinetic energy of the gas atoms in the system.